pi over 2, that's 1. We just did that on the unit circle a second ago. So we get 1 minus 1 on top. That's headed towards 0. Let's see. 2 times pi over 2 goes here. The 2's cancel. That's just pi. Cosine of pi. So go back here. Pi is here. That's our angle pi. Cosine is the x-coordinate, which is -1. So this right here goes to -1. 1 plus -1 is 0. So we have the appropriate form that we need for L'Hopital's rule. So I can apply it. Limit theta goes to pi over 2. And derivative of the top. We have two different terms. Derivative of 1 is 0. Derivative of sine is cosine. But we have a minus, so minus cosine theta. Over derivative of 1 is 0. And then be careful here because this is chain rule. We have cosine of something. Derivative of cosine of something is negative sine of that something times derivative of what's inside. Derivative of 2 theta is 2. And now we're going to try again. So theta goes to pi over 2. Cosine of pi over 2 is 0. -0 is still 0. So we get 0 on top. And now let's try this. We're going to plug pi over 2 in right here. So if we plug in pi over 2 right there, 2 times pi over 2, we just get pi. And sine of pi is the y-coordinate over here. Oh, that's -1. Did I put -1 earlier? I don't know. It's supposed to be -1. I think I might have put 1. I don't know. Okay, sine of pi is going to be 0. So this whole thing right here is 0. And then times 2 is 0, so the bottom is 0. So we still have 0 over 0. And that means that the L'Hopital's rule did not fix it yet. Let's try and take the derivative again, or let's try L'Hopital's rule again, apply the rule twice. The reason we can apply the rule again is because we still have 0 over 0. If this came out to be something like, 4 over 2, or sorry, like 4 over 0, then we would have to do something else. But the fact that it's 0 over 0 means we can apply the rule again. So this is going to be equal to the limit as theta goes to pi over 2 of the derivative of the top. So derivative of cosine theta is negative sine theta, but then we have minus, so it's going to turn into a plus sine theta. Over, now on the bottom, remember this right here is really -2 sine 2 theta. That's what that is. Just move this 2 out front. And this is a constant. I'm going to be taking the derivative. It's going to come for the ride. -2 times derivative of sine of something is cosine of the something times the derivative of what's in here, which is another 2. And now I try again. So if I let theta go to pi over 2, sine of pi over 2, there's where we are. That's not where we are, sorry. Sine is the y-coordinate, so this is just going to be 1 over, all right, cosine of 2 times pi over 2, 2 times pi over 2, we've done this several times now, it's just pi. Cosine of pi, that means we're here, is the x-coordinate, that's -1. So this right here is -1. So I have -2 times -1, which is 2, times 2 again, this is 4. So we should get 1/4. That's it, we're done. So that's our first example where we had to apply L'Hopital's rule twice. Seems dark in here. Just make sure all these lights are on. That was number 7. Number 8's next. Just double check these lights. Ah, thought there was a light off. Okay. Number 8. Limit as theta goes to pi over 2 of 1 minus sine theta over cosecant theta. All right, so theta is going to go to pi over 2. Sine of pi over 2 we already said was 1. 1 minus 1 is 0. So this is headed towards 0 over, now cosecant of pi over 2. So let me see what happens here. Cosecant theta is really 1 over sine theta. And if I plug in pi over 2, sine of pi over 2 is 1. So we should get 1 over 1. Let me see if I wrote that down right. Yeah? Okay, I'm just double checking this because we don't have to do anything here. Here's pi over 2. We got the x coordinate and the y coordinate. So sine of pi over 2 is the y coordinate. That's 1. 1 minus 1 is 0. Cosecant is 1 over sine. Sine of pi over 2, we just said is 1. That's 1 over 1. So this bottom part is just 1. 0 divided by 1 is 0. There's nothing to do here. There's no L'Hopital rule at all. So I think this problem is just to illustrate, don't go trying to do L'Hopital on everything, because if it's not 0 over 0 or infinity over infinity, you can't use the rule. And in this case, we just have a nice clean answer and we're done. All right, number 9. Limit x approaches 0 from the right. Of natural log x over x. All right. So let's see what happens here. What happens to the natural log function as we approach 0 from the right? So let me graph the natural log function. Natural log function looks like this. So as we approach 0 from the right, this heads to negative infinity over, and then the bottom is headed towards 0. And it's coming in from the right, so it's little positive numbers. So what happens here? There's two ways you can look at this. Well, here's one way. You can rewrite this as 1 over 0 times negative infinity. So just kind of like sliding this off to the side. And we can ask ourselves, okay, what happens if you have a fixed number that's positive, 1 is positive, over a number that's getting smaller but is also positive? So remember, if you have fixed over 0, that's going to be infinity, negative infinity, or does not exist. In this case, since the numerator and denominator are both positive, this is going to go to positive infinity. If you take a huge positive number, right, and multiply it times a very huge negative number, you're going to get a very huge negative number. So you're going to get negative infinity. So this is another illustration where we did not use L'Hopital's rule. In fact, we could not use L'Hopital's rule because we did not have what we needed. All right, number 10. The problem with L'Hopital is that people will start getting like so happy about it that they just start doing L'Hopital on everything, and you can't. All right, limit as x goes to infinity of natural log of the square root of x over x squared. All right, so what happens if I start letting x go to infinity here? This gets huge. Square root of infinity is still infinite. Natural log of infinity means, if we look at the natural log function, which we just looked at, what happens is we start going out this way. What happens to the natural log function? Well, it starts to grow without bounds, so it becomes infinite also. So the top here is headed towards infinity. And then, of course, infinity squared is going to be infinity, so we get infinity over infinity. We are allowed to use L'Hopital's rule because we have this. So I'm going to bring in L'Hopital's rule. And